Imagine two perfectly synchronized clocks, each ticking away in perfect harmony, their hands moving in unison second by second. These clocks are so precise that even the tiniest fraction of a second is measured with absolute accuracy. Now picture them as the ultimate symbols of timekeeping. So reliable that scientists trust them to define the very nature of time itself. Now let's take these two clocks and separate them. One remains safely on the ground, perhaps in a laboratory, while the other embarks on an extraordinary journey. It boards a jet airliner soaring high above the clouds, circling the globe at incredible speeds. As the plane races through the sky, the clock on board experiences a world very different from its twin left behind. After this journey, the traveling clock returns to its original location. You might expect quite logically that both clocks would still be perfectly synchronized, their hands pointing to the exact same time, as if nothing had changed. After all, they started together, and time should be absolute, right? But in 1971, a groundbreaking experiment by Joseph Haffel and Richard Keating challenged this very assumption. Known as the Haffel-Keating experiment, it was a bold test of one of Einstein's most mind-bending predictions. The scientists set out to see if time itself could be altered by motion, something that seemed almost impossible at the time. To conduct their experiment, they used some of the most accurate timepieces ever created, atomic clocks. These clocks were flown on commercial airliners around the world, while identical clocks remained stationary at the U.S. Naval Observatory. The scientists meticulously tracked every second, ensuring that no detail was overlooked. According to Einstein's theory of relativity, time is not fixed. Instead, it can stretch or shrink depending on how fast you're moving. The faster you travel, the slower your clock ticks compared to one at rest. This idea, once considered science fiction, was about to be put to the ultimate test. When the airborne clocks finally returned, the results were astonishing. The clocks that had traveled on the jets were no longer in perfect sync with those that had stayed behind. The difference was tiny, just a few nanoseconds, but it was real, measurable, and exactly what Einstein had predicted decades earlier. This simple yet profound experiment revealed a startling truth. Time is not a universal constant. Instead, it's personal, shaped by your speed and your journey through space. Each of us, in a sense, carries our own unique clock, ticking at its own pace depending on how we move. The implications of this discovery reach far beyond the laboratory. Today, technologies like GPS rely on this very principle. Satellites orbiting Earth move at high speeds and experience time differently than clocks on the ground. Engineers must constantly adjust satellite clocks to account for these relativistic effects, or the entire system would quickly become inaccurate. Without these crucial adjustments, your GPS would be off by kilometers every single day, making navigation unreliable and frustrating. The world as we know it, our ability to find our way, track packages, or even synchronize financial transactions, depends on understanding the flexible nature of time. So, the next time you use a map app to find a coffee shop or navigate a new city, take a moment to appreciate the genius of Einstein and the scientists who proved that time is not as rigid as it seems. Thanks to their work, we now know that time bends, stretches, and adapts to our journey through the universe. How can time slow down with speed? This question has puzzled scientists and thinkers for centuries. The answer lies in the very fabric of our universe. To understand, we must rethink space and time. They are not separate entities but are interwoven in a complex tapestry. Einstein saw them as a single four-dimensional fabric, space-time. This revolutionary idea changed our understanding of the cosmos. This isn't just a concept, it's the universe's stage. Everything that happens within this space-time fabric. Einstein proposed space-time is flexible, like a cosmic trampoline, bent by mass and energy. This bending is what we perceive as gravity. Imagine a bowling ball on a trampoline creating a dip. This is gravity. Objects move along these curves, following the paths laid out by the warped space-time. Gravity isn't a force pulling objects, but the curvature of space-time caused by mass. This curvature directs the motion of planets, stars, and even light. Planets and stars create wells in space-time, affecting paths and time flow. The more massive the object, the deeper the well, and the more pronounced the effect. The stronger the gravity, the slower time passes, gravitational time dilation. Near a black hole, time can slow down dramatically compared to Earth. Time runs at different rates depending on gravity's strength, a physical reality. This phenomenon is crucial for technologies like GPS, which must account for these differences to provide accurate positioning. Gravity's effect on time isn't just for astronomers, it happens on Earth. A clock on a mountaintop ticks faster than one at sea level due to weaker gravity. This is measurable with atomic clocks, proving time's relativity. Now consider a black hole, where gravity creates a deep space-time well. Near a black hole, time dilation is extreme. A clock appears to freeze at the event horizon. For the clock, time passes normally, showcasing relativity's mind-bending effects. Black holes test our understanding of gravity and time, revealing the universe's pliability. The Big Bang model has guided our understanding of the universe's birth. The James Webb Space Telescope, JWST, tests this model, peering back in time. JWST sees galaxies as they were billions of years ago, like a cosmic time machine. Surprisingly, it finds early galaxies that are big and mature, challenging our models. These discoveries don't disprove the Big Bang but prompt re-evaluation. How did galaxies form so quickly? Did stars ignite earlier? JWST pushes our understanding of cosmic evolution, hinting at unknown early universe factors. These findings suggest our cosmic timeline might need revision. Enter quantum mechanics, where our everyday understanding of time begins to unravel and things get truly strange. In the quantum world, the rules that govern reality are unlike anything we experience in our daily lives. Here, time is not always a steady, predictable flow. Instead, it can behave in ways that seem almost magical or paradoxical. Quantum mechanics governs the universe's smallest scales, where particles like electrons and photons follow fuzzy, probabilistic rules. Instead of moving in straight lines or predictable paths, these particles exist in a haze of possibilities, only settling into a definite state when we observe them. This uncertainty is at the heart of quantum physics, and it challenges our classical ideas about how time should work. In this realm, time isn't just a simple arrow moving from past to future. It's deeply connected to quantum entanglement, where two particles can become linked so that the state of one instantly influences the other, no matter how far apart they are. This strange connection seems to defy our normal sense of time and space. Unobserved particles exist in a cloud of possibilities, a superposition of all possible states. When we measure or observe them, they suddenly choose a state, collapsing into a single outcome. This act of observation appears to play a role in how time unfolds at the quantum level, making the flow of time feel less absolute and more dependent on what we know. Some physicists suggest that time itself might emerge from the way quantum events resolve uncertainty. In other words, the passage of time could be a byproduct of countless quantum decisions happening everywhere, all the time. This idea is still being explored, but it hints at a universe where time is not a fundamental ingredient, but something that arises from deeper, more mysterious processes. At the quantum level, processes can sometimes move forward or even backward in time, at least mathematically. This reversibility is very different from our everyday experience, where time only seems to move in one direction, from past to future. The arrow of time, which we usually link to the increase of entropy or disorder, remains one of the biggest mysteries in physics. Why does time seem to have a preferred direction, and what sets it apart from the timeless world of quantum mechanics? Uniting Einstein's theory of relativity, which describes the universe on the largest scales, with quantum mechanics, which rules the smallest, is one of the greatest challenges in science. Physicists are searching for a theory of everything that can explain both gravity and quantum phenomena in a single framework. If we succeed, this new theory could completely redefine our understanding of space and time, possibly revealing hidden dimensions and rewriting the very fabric of reality as we know it. Let's review our cosmic journey. We began with clocks proving time's relativity, then explored Einstein's space-time fabric. Gravity's effect on time is measurable, becoming extreme near black holes. The James Webb Telescope challenges our cosmic timeline with mature early galaxies. Quantum mechanics adds complexity, with time linked to probability and uncertainty. The disconnect between relativity and quantum mechanics suggests we're missing something profound. Our understanding of time and space is not the final word. We're explorers, venturing into the universe's mysterious interior. We're at a crossroads in our cosmic journey, realizing how much we don't know. Is time a fundamental river or an illusion? Are past, present, and future simultaneous? The James Webb Telescope's findings prompt questions about our origins. Could the universe be older, or did it undergo cycles of expansion and contraction? Bridging relativity and quantum mechanics into a theory of quantum gravity is crucial. This theory might reveal spacetime's true nature, with discrete pixels or extra dimensions. The universe's true nature might be stranger and more beautiful than imagined. The quest for answers continues, with discoveries waiting in the cosmic darkness.